Hello everyone, Mrs. Hansen here, continuing our lessons in the Electrochemistry chapter with a clear focus today on a Voltaic cell called a Galvanic cell as well, either word or either vocabulary term to talk about common batteries. We'll begin by describing the function of a galvanic cell and its components, and we'll work towards writing out cell notations that symbolize the composition and the construction of these galvanic cells. Let's begin with an example we talked about in a previous lesson, just a single replacement reaction. We mentioned that a single replacement reaction takes an element and reacts it with a compound to produce a new element and a compound. And we focused on this particular picture earlier in that lesson. In this first picture, we see elemental copper just coiled in a loop, probably around a pencil to make a spring. And in the test tube, I see a solution of aqueous silver nitrate. So we have solid copper in a solution of silver nitrate, AgNO3AQ. Now notice that copper and silver are both metals. And if copper is strong enough, more active enough, it will displace the silver, pulling it out of solution and going on to form elemental silver, and pulling the copper into solution, making an aqueous copper 2 nitrate color. And you can see as time goes by, the silver metal is going into solution. And you can see this silver starting to plate out on the original copper, and so much so that the copper now in solution as a copper ion is a blue color. Notice how the solution is now blue, and what's plating out is solid silver coating itself on that original copper spring. And so this single replacement reaction we also know was a redox reaction. When we eliminate the spectator nitrate, we could see that the redox reaction shows solid copper reacting with aqueous ions of silver to form solid silver and pulling the solution into the copper ion. So our balanced equation where we eliminate the nitrate simply shows a transfer of charge. The copper started at oxidation state 0 and went to a +2. We know that that is a loss of electrons called oxidation. So the half reaction for this oxidation would show elemental copper, and on the other side, aqueous ion of copper. And we know to balance this, we have to balance by both mass and charge. To the more positive side, I'll add 2 moles of electrons. There is the half reaction for the oxidation, the loss of electrons. Now the opposite of that would be gaining electrons. We started with 2 moles of aqueous ions of silver, added 2 moles worth of electrons to create a neutral elemental form of solid silver. We know that this must represent the gain of electrons or reduction. The +1 charge went to a neutral 0. That is the half reaction of gaining electrons becoming more negative on the number line. And you can see why then we had 2 in front of the silver to keep those balanced. We had to balance by both mass and charge. If 2 electrons were lost from the copper, the silver must gain 2 electrons. So this part is review of a single replacement reaction, also known as a redox, and we've been practicing in the last a ton of writing out these equations. But in the next step, when we think about doing useful work with a redox reaction and actually generating electricity, generating a voltage that we can capture and perform work with, we end up separating the 2 half reactions, physically separating them into separate containers and preventing them from even coming into contact. So consider this same reaction, but one that uses a device to prevent that physical contact between the reactants. And the transfer of electrons between the two halves is occurring between a wire, an external circuit that contacts the separated reactants. So let's look at this very carefully. I know that you're going to be asked to draw one of these. We're going to kind of go through the same process together here and draw it. In one half reaction, which is just a beaker filled with a solution and an electrode placed in it. An electrode will either be a cathode or an anode depending upon the reaction. In this particular picture, this is pure copper metal. Now in the last picture it was a wire of copper coiled in a spring, but here generally an electrode is just a flat piece of metal. And in the solution we have a copper nitrate solution. And I'm going to go through and kind of write down here, you have a 1 molar standard concentration for these cells is 1 molar of copper 2 nitrate. So you'll write that as CuNO3 taken twice. So that's the solution. Usually in the lab you'll have a little alligator clip that connects a wire, and that wire then is connected to a voltmeter, so you can read voltage here in this battery. And then it continues on into the next half cell. And again, this is just another beaker. This beaker contains an electrode made of pure silver. So this is just a piece of silver metal. And in solution is its ion, Ag+. So underneath here, the solution now would contain a standard concentration of 1 molar silver nitrate. We understand that the copper, if you go back and look at this reaction, remember the half reaction? The copper was losing electrons. It was the oxidation half reaction. So when I think about what's happening in this cell, the half reaction that's occurring is the solid copper going to aqueous ions of copper and generating electrons. What's happening in the other cell? We said this was oxidation. Well, what's happening in the other cell is called reduction. This is where the silver ion gained the electron to form silver metal. This was the half reaction of reduction. Now, right now, my picture is incomplete because when the electrons are generated over in this half cell, they are moving through this current by a potential difference, and they are entering into this half cell, but right now my circuit is incomplete. Right now, the voltmeter would read 0. I have to complete the circuit, and to do that, I have to allow ions to move past from one back into the other half cell. And what I'm trying to draw here is what's called a salt bridge. Now in the lab, I often use just a salt-soaked filter paper, a piece of filter paper that's been soaking in salt water to just lay across one beaker to the other. So that makes a great salt bridge. Something that is, here's a hollow tube in this picture. They have a hollow tube packed full of sodium nitrate, which is a salt. The salt bridge serves a very important purpose that we're going to further in just another moment. But as I try to draw, as you are on your paper, I wanted to go through some of these highlights of this battery, this galvanic cell or voltaic cell. Now let's pick up some further vocabulary. We drew on the left side the oxidation reaction. Oxidation always occurs in the anode half cell. On the right side, we drew reduction. And you should know that the cathode is the half cell where reduction occurs. And by standard notation, we always write the anode on the left and the cathode on the right for voltaic cells. Now I'm emphasizing that voltaic and galvanic are the same thing. Galvanic cell is an honorary name named after a scientist, Galvani, and a voltaic cell simply comes from the voltage, the unit that we measure potential difference in. But do hear those as the same term. At the end of this chapter, when we flip directions for non-spontaneous reactions with electrolytic cells, this whole thing flips around and the cathode will be on the left and the anode will be on the right. But we're not there yet. For standard notation on a voltaic or galvanic cell, cathode is on the right, anode is on the left by standard conditions. And here I said we have this external circuit. The electrons are being generated in the oxidation half cell. And so you see the current beginning to flow from the anode into the cathode in that particular direction. So this is the electron flow, kind of in a clockwise fashion from anode to cathode. Think of the chemistry that's happening here. We said in the anode half reaction, aqueous copper ions are being formed. See how the arrow is coming out? So over time, this plate of copper, this copper electrode is actually losing mass as the solid copper turns into aqueous ions of copper and dissolve into the water. Now, as we generate more and more copper plus 2 ions, we have to keep the charge balanced, and that's the job of the salt bridge. Now, the salt inside of this packed piece of glass tubing, sodium nitrate, it's made of 2 different ions, isn't it? You have a sodium ion and a nitrate ion. If the anode, the oxidation half cell, is generating more positive charge as time goes by, as the electrode is going from solid to aqueous ions, we have to neutralize those positive charge, and that's what the nitrate is migrating from. The salt bridge, negative ions of nitrate, are going right into this solution to balance the positive charge that's being generated, keeping it electrically neutral. Let's turn our attention over here to the cathode, where we said cathode is the site of reduction, and therefore we know that electrons are being gained. Notice the electrons are coming into solution, therefore they're being gained. But in terms of the chemistry, the solid silver is actually having more mass added to it as time goes by. Aqueous ions of silver are plating onto that copper, onto the silver electrode. So this is actually losing mass over time. The copper is degrading into aqueous ions, and this is actually gaining mass over time as the aqueous ions plate onto that plate and kind of add mass as pure silver. So if I'm removing these positive ions, right, we have to balance the charge, and that's the job of the sodium. For every 1 silver ion that's being plated onto the electrode, I have to balance that missing charge, and a sodium ion will migrate in to this solution to keep an electrically neutral charge overall. So, because we add copper ions in oxidation, the nitrate neutralizes those. The flow of anions from the salt bridge is towards the anode. On this side, we see that electrons are being gained. The silver ion is plating out. Therefore, we balance the charge with the cations flowing into solution. From the salt bridge, the cations migrate towards the cathode. And all of that is done to keep that electrically neutral overall. And we've just drawn our first simple battery, haven't we? We have introduced terms such as anode, cathode, salt bridge, voltage, all kinds of good stuff. Now this is the same picture. I just wanted to make sure I rewrote this very clean so you could see your notes in comparison to the notes I hand wrote on the previous slide. Let me emphasize some points that we discussed. We know this is a picture called a galvanic cell. A galvanic cell is composed of two half cells. Now remember, we separate the two half reactions. We have an anode side and a cathode side. We must complete the circuit to have electrons flow. We do that with some wires. So an external circuit. Typically, you're going to see a pair of alligator clips just in the lab to create a simple circuit. You'll use some alligator clips and some wires. On the left side, we always have the anode. By convention, we will always write the anode. We know that oxidation occurs on the left side by convention. Now, I know I can walk around this battery and look at it from any angle, but when I'm drawing it, draw the anode on the left, the site of oxidation. And we talked about the copper ion entering the solution. From the metal, it goes from solid to aqueous copper. Well, that makes sense because it's oxidation. Copper must be losing electrons to generate an electrical current. The flow of electrons is leaving the anode and going towards the cathode. Cathode by convention is always on the right. It's the site of reduction. Notice that the silver ion is coming out of solution and plating onto the silver electrode. Therefore, it's gaining weight. The silver is the cathode. To keep this electrically neutral, we see the positive ion migrating out of the salt bridge to balance the charge so that as silver leaves as its ionic form, the sodium will then enter to keep it charged, balanced. So remember, the site of reaction, really where is the redox occurring, is at the interface of the solution to the metal anode or the metal cathode. So it's the interface between the half reactions where we actually have redox occurring. And to keep these reactants separate but maintaining the charge balance, the two half reactions have to be bound together by a tube or some sort of salt bridge that contains a positive ion and a negative ion to migrate and keep the charges balanced as the electron circuit is completed. So it's usually either a tube filled with an inert electrolyte, such as sodium nitrate. I mentioned in the lab, it's very simple to do a salt-saturated piece of filter paper. Just soak a piece of filter paper, coffee filter, put it into salt water, get it wet, and it will complete a circuit just fine. So in this reaction, we've looked again, the same picture, but I want to talk next about how we can take this complex picture and write about it in easy enough cell notation, shorthand, if you will, for all the chemistry that's going on in this picture. And that's what we refer to as standard cell notation. So here's three kind of components of what standard cell notation is telling you. It says all relevant components of each half cell are represented by their chemical formulas, if they're compounds, or elemental symbols if they're elements. So in this particular side, this would be elemental copper. In this particular side, this is elemental silver. In solution, we have a copper +2 ion. In solution here, we have an aqueous ion of silver. The interfaces between component phases are represented by vertical parallel lines. And then if two or more components are present in the same phase, we separate their formulas by commas. And by convention, we write the anode on the left. Anode is the site of oxidation. And on the right, we write out the cathode, which is the site of reduction. Now, this is just a little way that I remember it. You know, see how anode and the term oxidation both start with vowels. That helps me remember that those two are associated with each other. And the term cathode and the term reduction both start with consonants. C and R are both consonants. A and O are both vowels. It helps me remember which term associates with which electrode. Maybe it will help you too. So let's take a look. We know we start over here on the left side. What is in the anode? The anode is the site of oxidation. So the chemistry says that copper solid is losing 2 electrons to form its aqueous ion, copper plus 2. This is the chemistry of the anode. So how do we represent that chemistry in standard notation? We said the elemental symbol of copper, with its S for solid, is going to be separated by its interface. That's that parallel line there, separating that phase there. And what is the solution in that? Well, the solution is copper 2 nitrate. It says we have 1 molar of copper 2 nitrate. So here we have the standard notation written right here. I should have aqueous, the phase of matter. This is representing the anode left half cell of this battery. Notice what you see next. This double parallel line represents the salt bridge. So I'm separating physically the anode by the salt bridge to what's happening over here in the cathode. Now the cathode is the site of reduction. That means the silver ion is plating into solid silver by gaining an electron. So that's the chemistry going on in that half cell. We're gaining electrons to plate out solid silver. We have to represent that in the order of the reaction. So the solution comes first. This is an aqueous ion in 1 molar of silver nitrate. Notice I'm writing the solution first and then separated by, because it's an interface, to solid silver. I just wrote out the standard cell notation for the battery that we've been drawing. The anode to the left, I use a parallel line to separate the phases that I find in there. I want to emphasize, since anode is oxidation, copper metal going to copper ion is oxidation. The order which you write must show oxidation. Then the salt bridge, the double line. And now in the cathode we have reduction. Notice that I have the solution first, the aqueous ion of silver being reduced to elemental silver. So it matters the order with which you write the solutions in the solid. On the left side, the solid comes first, then the solution. On the right side, the solution first, and then the solid, because that's the change. Oxidation on the left, reduction on the right. All right, so I wanted also to emphasize we do not balance the equation in the standard cell notation. In other words, I don't put coefficients here. There's no 2 in front of the silver, even though I know overall the reaction would need to be balanced with coefficients, but we do not include coefficients to balance equations in the standard cell notation. Okay, that's a lot to digest. Shall we practice? Here's a picture. Let's kind of get our bearings here. On the left side, I know by convention that this will be the anode, which is the site of oxidation. And on the right side, this half cell will always represent the cathode, the site of reduction. What's going on in the anode side? Well, I could see magnesium. So this is a coil of elemental magnesium just kind of twisted in, and it's in a solution of magnesium chloride. So again, notice the salt bridge is a glass-filled tube packed with sodium chloride, table salt. As the positive ions from magnesium turn from solid to aqueous ions, we need to balance that charge. So the anions come into the solution from the salt bridge to keep it electrically balanced. Over on this side, what's going on? Well, let me back up. I'm sorry. Let's kind of write down what we had so far. We had magnesium in the solid phase, and then a line to separate the phase with a 0.1 molar magnesium chloride aqueous solution. So I just wanted to, before I moved on, I wanted to back up and make sure we wrote out the cell notation for what we saw in the anode. Alrighty. Now, what's going on over here? Something unusual is happening from what we saw in the first example. Right here is the reduction half reaction. I'm changing an aqueous iron plus 3 into an aqueous ion plus 2. These are both aqueous ions. How in the world am I supposed to hook an electrode, an alligator clip, to an ion that's in solution? And the answer is you really can't. So what we need to do physically is use an inert metal such as platinum or palladium or titanium. Of all the things I've just named, platinum and palladium are probably the least expensive. So we use an inert electrode, and that's what PT is. This is an element. Look it up on the periodic table. It's platinum. But it's not really part of the chemistry because it's an inert metal. But what it allows us to do is to have on the surface of this coiled platinum wire reduction occur. And at that site, we're seeing a gain of electron for the reduction half reaction. One electron is being gained and turning the plus 3 into the plus 2 charge. So how do we write about that? Well, remember, in solution, on the cathode side, we write reduction reactions with solutions first. I have present a 0.2 molar iron 3 chloride solution in the aqueous phase. I also have in solution, notice that's a comma, I also have in solution 0.3 molar iron 2 chloride, and that's also in the aqueous phase. These are both solutions. So I can clearly see the reduction is occurring. I went from a plus 3 to a plus 2. That is reduction. But where is that surface occurring? Where is the actual reduction occurring? Well, it's occurring at the platinum inert electrode. So notice where my line comes in is separating the aqueous phase to the inert electrode called platinum, PT. And that's how I'll designate this cathode half cell. In solution, we have iron 3 chloride and iron 2 chloride, all connected to an inert electrode called platinum. And I said platinum tends to be the most often used. It's easily purchased. It comes in a nice coil, just like copper does. So let's make sure we see that magnesium here would be called an active electrode because it is the element that is being oxidized. But platinum is called an inert electrode because it is not the element that's being reduced. The element being reduced here is iron. So think about this reaction before I leave this page. On the oxidation side, we had Mg solid turning into Mg aqueous ion, releasing 2 electrons. We called this oxidation. This is what occurred at the anode. On the other side, which would be the cathode, we had an iron plus 3 aqueous ion gaining an electron to form an aqueous ion of iron, that's a mouthful, plus 2. So that's reduction. That's what occurred at the cathode. Now to balance that, I know I would distribute a 2 through this equation so that the loss equals the gain. Combining those back on, our complete redox reaction would look like solid magnesium reacts with aqueous iron plus 3 to form aqueous magnesium and 2 iron plus plus 2s. There, I got it. Did I balance? Overall, on the right side, we have a plus 4, 4, 6, plus 6 on this side. This is right. So here we have 2 units of a plus 3 is plus 6. Here we have a plus 2. 2 units of a plus 2 is plus 4. Combined all together, plus 6. So yep, we're balanced by both mass and charge. The reason I'm emphasizing, when you have an aqueous reactant and it remains aqueous as the product, as this example did, just to kind of clarify, there is no way you can, hook an alligator clip to complete a circuit. This is your clue. This is how you know you need an inert electrode involved to complete the circuit and give a site for the electron transfer. And that inert electrode most often will be written as platinum. Okay, great. Good work. Let's keep processing examples. Here I'm given, I just clipped this right out of our textbook. It says a galvanic cell is fabricated by connecting 2 half cells with a salt bridge. So I'm getting an image. I have a beaker, a second beaker, and the beaker will contain solutions as well as electrodes. I know that I'll hook them together with an alligator clip, one to connect each of those metal strips. And typically you'll see a voltmeter, so we can measure how much electricity is being generated from one half cell to the other. We also know that you'll complete the circuit with a salt bridge. And that's kind of just a general outline of how we always get started drawing a simple cell. That I will always place the anode to the left, and I'll always place the cathode to the right. The anode is the site of oxidation, and the cathode is always the site of reduction. Okay, so that's so far. 2 half cells with a salt bridge, got it. One in which a chromium wire is immersed in 1 molar chromium chloride. Here's my chromium wire in a solution of copper 2 chloride. No, oh, right here, chromium 3 chloride. And it says it's 1 molar. On the other side, we have a copper wire, and it's submersed in a 1 molar copper 2 chloride solution. Assuming the chromium wire functions as the anode, write the schematic for this cell, which is drawing this picture. When you see this, it says draw the picture, along with its equations for the anode and half reaction cathodes and the overall cell reaction. So the anode site, the chromium starts as a solid. It is separated by a parallel line to represent the interface, the site of this oxidation. And we have a 1 molar chromium 3 chloride solution. Make sure you remember it's aqueous. Separated by a salt bridge. On the other side, we have a 1 molar copper 2 chloride solution separated by elemental copper. Remember your phases there. I have to remember it's aqueous and solid. Verify. Chromium went from 0 to +3. That is oxidation. Oxidation occurs in the anode. That looks good. Over here, let's verify. Copper went from a +2 to a 0. That is reduction, and that occurred in the cathode. So I've written them in the proper order, making sure that I always check that anode represents oxidation. I should become more positive as I write out the cell notation. Cathodes represent reduction, so I should become more negative as I represent those solutions. Now, the other thing I notice is I don't need an inert electrode because I have chromium solid going to aqueous ion. I can definitely place an electrode on this hunk of chromium metal. Same over here. I can hook an electrode to a solid copper piece of metal. So I don't need anything inert to take care of that. They can serve as their own electrodes. Now, how about the overall equations? Chromium metal went on to form chromium +3. How do I know it's a +3? When you look at CrCl3, you see that you uncrisscross. Chromium must have been a +3, chloride a -1. That's why it's written CrCl3. And therefore it lost 3 electrons. This is your oxidation half reaction. In reduction, notice here it's copper 2 chloride. Chloride's a -1, therefore copper must be a +2. So here you have copper ion +2 gaining 2 electrons, forming elemental copper. That's your redox 2 half reactions. Here's your loss of electrons oxidation, gain of electrons reduction. Leo must equal Gur, so I need to distribute a 2 and a 3 respectively when I add those two equations back to write the net equation overall. 2 solid chromiums reacts with 3 aqueous ions of copper +2 to form 2 aqueous ions of chromium +3 and 3 solid coppers. We are balanced by both mass and charge. The number of atoms on both sides are the same. That's the coefficients. And the overall charge is the same as +6 on both sides of the equation. We're balanced by both mass and charge. You want to pause and try one on yourself? Give yourself some think time, pause the video, and come back when you've had a chance to try this problem. Welcome back. The question asks us to write out the schematic for a galvanic cell whose net equation is provided below. Omitting solute concentrations. We don't have the molarities given. Here I notice that tin +4 is going to tin +2. It's becoming more negative. There's my reduction half reaction. I have solid tin, zinc, Zn. This is zinc all day long, going from 0 to a +2, and that's Leo. That's your oxidation half reaction. So my schematic would show in my anode half cell, where the oxidation occurs, zinc in its elemental form can hold on to an alligator clip, and I can attach it to a voltmeter and bring it over to the second half cell, the cathode, where the site of reduction occurs. I know that I'll have to complete my circuit by putting in a salt bridge. But what about the electrode going on in the cathode side? Notice that I have an aqueous plus 4 turning into an aqueous plus 2. That the reaction itself that's occurring has tin plus 4 turning into tin plus 2. These are both aqueous ions, and therefore they're both in the solution. So what am I supposed to hook the alligator clip to? Remember, this was the clue that I'm going to need an inert electrode, and I'm just going to put in platinum as my inert electrode, and you could just write that as PT, its elemental symbol. I know that I need that inert electrode because I can't hook an alligator clip to complete a wired circuit if both reactant and product are in the aqueous phase. So this is the schematic. Let's write the standard cell notation. And it's telling us that, we don't necessarily know what the solutions are. So all I can do is this. The zinc solid separated with the aqueous ion of zinc. That's all I know from this particular description. I don't know the identity in the salt bridge to know the negative ion, and they certainly didn't tell me the molar concentration. So it's just kind of omitting some things. We're going to separate out by a salt bridge. In solution, we start with Sn plus 4, aqueous phase, and then a comma to separate the Sn plus 2 aqueous phase, and then the line with the electrode platinum. And that inert electrode is being used as the site of reduction for the aqueous ion of plus 4 turning into plus 2. I picked this one on purpose to remind us if you have an aqueous phase for both reactant and product, we need to have an inert electrode. Let's talk more about electrodes and cell potentials. We're going to work to describe and relate the definitions of electrodes and cell potentials to interpret electrode potentials in terms of their relative oxidant and reductant strengths, and end up calculating cell potentials and predict if redox spontaneity using that electrode potentials chart. In your test-taking tool pages, you need your standard reduction table. And I've done a lot of clipping out as we progress through, but just so you can see where I'm pulling these numbers. So we're moving to quantize, to calculate cell potential. We've done a great big, lecture here on how to draw electrolytic cells, and Voltaic cells, galvanic cells, kind of get an idea of what it means to be a half reaction. I've been drawing what these little voltmeters are. I want to learn how to calculate what the voltmeters would say when I set up two half reactions and connect them, completing a circuit. When electrochemical cells permit relative redox activity, we're quantifying that with a measurable property known as potential, commonly called a voltage. Now, a definition of a volt, we need to know this for future calculations as well. The term volt is defined as a joule per coulomb. 1 joule of energy per coulomb of charge. You can find the value of a coulomb by taking 1 mole, or Avogadro's number, of electrons, and that's where that value would come from. So again, the definition, joule per coulomb, in a few lessons from now, we're going to be able to use that unit to go through some dimensional analysis. On this slide, I'm really understanding what potential means. Potential between two half cells is the difference in voltage generating a current. And that potential reflects a driving force between the reactants of our redox. We measure a difference from one side to the other side in these two half cells, call it cell potential. The E cell, this is the voltage of a cell. A cell consists of two half cells, doesn't it? We have an anode and a cathode. And what we do is take the cathode minus the anode voltage to come up with the overall cell's voltage. Cathode minus anode. You can think of this as reduction minus oxidation. That's a critical formula in understanding the next set of calculations. So these standard cell potentials, let's talk a great deal about where do these numbers come from on your standard chart. Well, the standard cell potential measures when both half cells are under standard state conditions. I know this will pop up in multiple choice if you're lucky enough to get this. Know the conditions of standard states. And it's the same if we're looking at standard enthalpy change, standard any thermodynamic product. 1 molar concentration. So in the solution is a 1 molar concentration, 1 atmosphere pressure, standard pressure, and 25 degrees Celsius, which is 298 Kelvin units. These are just called standard conditions. These are the conditions in the lab when we generate voltage and measure it with a voltmeter at standard states. Now, since half reactions don't generate a voltage that you can measure, we measure potential difference. We have to have something to compare a half cell to. And that's the job of a standard hydrogen electrode. The standard hydrogen electrode. We've designated hydrogen to be the half cell as the reference for cell potential, assigning it a 0 voltage. The She cell, the standard hydrogen electrode. When I look on our reference table, the reference table for the reduction of hydrogen, it will be assigned 0 volts. Not to say that it doesn't have any electrical capacity, it's just we're going to call it 0 and compare every other elemental half cell to that standard. We have to call it 0. Things that are positive conduct more, are more active at losing electrons. Things that then fall below it would be less active. It's just the point of reference, assigning it a 0 voltage. So E cells, cathode minus anode. If you see these little circles up here, that represent standard state conditions. In a standard state condition, E cell is cathode minus anode at standard states. I want to focus on this She cell. I know you're trying to draw it a little bit as well. Now, we understand hydrogen is in a gaseous form. How in the world are you going to hook an alligator clip to a gas? Well, you can't. So, just as if you had ions in solution, we need an inert electrode for a gaseous reactant or product as well. Notice this is just a vacuum tube, and the vacuum tube has an opening, and usually you'll just see a rubber hose, and the hydrogen gas is being pumped into that vacuum tube. To complete the circuit, this is just a piece of platinum wire, and I can hook an alligator clip to the wire coming out of the vacuum tube. So you will always see an inert electrode involved with gaseous hydrogen, the She electrode, simply because we can't hook an electrode to a gaseous reactant or product. So we place the platinum wire inside the chamber that contains the gas to complete the circuit. And again, this is the platinum wire. It's the site where oxidation or reduction will occur depending on what's assigned to the other half reaction. So when we start looking at standard tables, this is the table I provide you as a test-taking tool. You probably have it printed by now. Or if you're reading through your chemistry book online, you can click Appendix L, and a long list of potential difference. The standard potentials are printed there for you as well. What's nice about the appendix in the OpenStax chemistry book is it's listed alphabetically. And notice the one that I give you does it by reactivity. So the most positive volts are listed at the top. Fluorine, of course, being the most active of nonmetals, gets listed at the very top. At the very bottom, the most active of metals gets listed at the bottom there, lithium. And the one in your chemistry text, Appendix L, doesn't list them by activity, but rather lists them alphabetically. Either way, we have sometimes we just have to look up standard electrode potentials for these half reactions. I also wanted to comment that these are all written as reduction half reactions. Regardless if the reaction that we want is oxidation or reduction, they're always listed with the electrons being gained on the left side. So that's why it's called a reduction table. These all show reduction half reactions. I wanted to point out here, this is the hydrogen she cell. In other words, it's assigned 0 volts. And every other half cell is compared to it. And just to kind of emphasize, we've been using copper quite a bit, which is just a common metal to put in a battery. When copper plus 2 forms elemental copper, it has a voltage of 0.34. Well, what does that mean? I wanted to show you how these numbers were generated. And so just with this picture, on one side, we place a standard hydrogen electrode, and this would be the anode since it's on the left side. And we create a battery where the cathode is what we're trying to measure, which happens to be here, the copper, simply because that's the one I selected a moment ago to show you where it comes from. When I compare the activity of the copper to the standard value she cell, the voltage reads 0.337. When I physically build this battery in the lab, hook it up to a voltmeter, it will read 0.337. That's exactly where this number comes from, 0.337. Here it's written as 0.34, based on comparison to the volts generated by the standard hydrogen electrode. So walking away from this, we know the she cell is the standard at which we compare all other half cells to. Let's try some problems. You'll find these quite simple, I hope. We're going to calculate the standard potential for this galvanic cell. Okay, well, first of all, let's get a picture of what's happening. Here I have a copper anode turning into aqueous ions of copper. So the chemistry here is solid copper turning into aqueous ions at a +2 charge and releasing 2 electrons. I know the flow of electrons is always clockwise and so forth. We know that this is the oxidation half reaction. What's going on in the other cell? Looks like I have silver over here. And this I know is the site of reduction, which means it's gaining electrons. The silver ion will gain an electron to form the solid silver. This is oxidation on the left. This is reduction on the right. To calculate the standard Ecell, the voltage of this battery, we take the standard reduction of the cathode minus the standard reduction of the anode. Cathode minus anode. Notice the C's are right next to each other. That helps me remember the order. Cathode minus anode, where the cell and the cathode both start with the same letter. It helps me remember the order. And I know that the cathode is the site of reduction because they're both consonants. And I know that the anode is the site of oxidation because they both start with vowels. I went into the reference chart and I just clipped the values that we needed. The silver has a potential of 0.7996. And I grabbed 3 different coppers to emphasize that you really have to be careful and find the exact reaction you're looking for. Did our copper plus 2 gain just 1 electron and form a copper plus 1? Did it gain 2 electrons and form elemental copper? Or did it start as a plus 1? What happened? Well, notice again, they're always written as reduction reactions. You just have to read it in the opposite order. This is what's occurring in this half cell. So the value there is 0.34 volts. Not this one, not this one. Make sure you're grabbing the correct half reaction. So the Ecell, at standard conditions, what's happening at the cathode, 0.7996 volts from the silver reduction, minus what's happening at the anode. That's the copper's value, 0.34. Do not change the sign to do your math. That's what the negative sign is doing for us. That's what we're subtracting. When I say cathode minus anode, this subtraction is already flipping the sign to turn the reaction the opposite direction. So do not change the sign given to you on the chart. I'm going to take 0.7996 minus a positive 0.34, and I will come out with Ecell for that particular battery. So what does this voltmeter say right there? Well, it'll say 0.7996 minus 0.34. It's going to say 0.4596. Guess I'm allowed 2 sig figs here. So it will say a positive 0.46 volts. Right there, positive 0.46 volts. And just to emphasize, this is a spontaneous reaction in the forward direction. I know that because I have positive voltage. The battery is generating a current with positive voltage. Therefore, I know just from last few chapters ago now that Gibbs free energy would be negative because it's a spontaneous reaction. So that's it. We look up the volts. Ecell is found by cathode minus anode. Do not change the sign. It is not stoichiometric dependent. Do not carry coefficients into these little subtractions. It's just very straightforward. Grab the number from the chart and subtract as is. Don't change a thing. Voltage is an intensive property, not stoichiometric dependent. Let's try another. Real simple. It says, same picture as before, but instead of the silver, let's replace it with lead. Alrighty, so over here on the cathode side, we have a different half reaction. We have a piece of lead in there, and the lead ion is being reduced. So again, Ecell at standard conditions is found by taking the cathode potential minus the anode potential. The cathode is the site of reduction. The anode is the site of oxidation. So cathode first, that would be the lead. It has a value of negative 0.1262 volts minus The oxidation, that's what's happening at the copper. From the chart, it has a value of positive 0.34. What is the Ecell, the standard voltage of this battery? I'll hit with you. Negative 0.1262 minus a positive 0.34. And my screen reads negative 0.4662. What did your screen read? That unit there is the voltage. And I just re-hit that because this tells me negative volts, that this is a non-spontaneous reaction in the forward direction. There's no volts being able to capture to do work. In other words, I would have to flip this whole circuit around, flipping what's the cathode, turn it into the anode, take the anode and convert it to the cathode to get positive voltage to make this reaction occur. It is not spontaneous as written. The negative volts would tell me that delta G is positive, meaning non-spontaneous. And that's really a good point to emphasize. I know a lot about the spontaneity of a cell. I know a lot about the equilibrium constant of a cell. And I know about Gibbs free energy of a cell by knowing its voltage as being positive or negative. Spontaneous reactions, as written, would have positive cell potential, positive volts. It would have negative delta G, exothermic, exergonic energy decreases in spontaneous solutions. And I know the equilibrium constant for the forward reaction would favor a large number. And, opposite, a negative voltage with a positive Gibbs free energy, which would favor the reactants side, all represent non-spontaneous reactions. And a moment ago, sorry, I'm sneezing, we wrote this equation out and came out with a negative potential difference. And I mentioned if you just flip the reaction around, instead of having lead plus 2 go to solid lead, that would be the half reaction. And instead of copper being oxidized, that's non-spontaneous, we have to flip the direction. We have to make the oxidation occur with the lead and the copper become reduced. When we do that, we get a positive voltage, and that makes it spontaneous in the forward direction. Let's bring that together with a simple question asking, is this spontaneous? I just snapped this from a quiz question. Is this reaction spontaneous in the forward direction? To answer that, let's decide what's being oxidized and what's being reduced. So I hooked together the two half reactions. Chromium goes from an elemental 0 charge to a +3. Here we recognize that's oxidation. Iron goes from +2 to 0. That's reduction. The Ecell is found by taking the cathode minus the anode, not stoichiometrically dependent. It's an intensive property. Do not flip the signs. Again, just stressing, I put the two C's together. That helps me. And these are both consonants, so that helps me just quickly remember definitions. What's being reduced? The iron. Since the iron's being reduced, it's written first, minus 0.447. What's being oxidized? We said that was the chromium. From the standard table of reductions, its value is negative 0.744. And let's hit that. I have a on for my calculator. Negative 0.447 minus a negative 0.744. And I get a positive 0.297. Yes, this reaction is spontaneous in the forward direction because, well, because I have a positive voltage. How about this one? Think this through with me. Is the oxidation of bromide ion by molecular iodine under standard state conditions spontaneous in the forward direction? Again, a quiz question. Bromide is Br negative. To be oxidized, the oxidation of bromide by molecular iodine. So what we're looking at is molecular iodine, I2. For bromide to be oxidized and iodine to force it, I'm going to write those half reactions. I just don't want to combine them just yet. Let's do this. I know that Br2 is the elemental form of bromine, and in order to create two, let's balance this out. This is the oxidation half reaction, and it's positive 1.0873 volts. When iodine forms two I negatives, it gains 2 electrons to do so. Therefore, this is the reduction, and it is 0.5355. So Ecell is what's happening at reduction first. That's the cathode. (1.0873 volts) for the anode. There. And what would that come out to be? 0.5355 minus 1.0873, and you get negative 0.5518 volts. So no, this is not spontaneous in the forward direction. Quickly, if you were asked to write that spontaneous reaction, you would need to convert what's being oxidized and reduced. So to make it spontaneous, there's the spontaneous reaction. Instead of having bromine oxidized, bromine is being reduced. And now I would end up the same equation. Switching what's positive and what's negative would have the same value, but now a positive voltage at the end. And so this would be the spontaneous direction, but as we were asked in this original question, it is not spontaneous. The oxidation of bromide by molecular iodine is not a spontaneous reaction. We're going to kind of bring together in our final closing here the potential, free energy, and equilibrium relationships. Our goal is to explain that the relations between potential, free energy change, and equilibrium constants, tying these all together. We'll perform calculations involving the relations between cell potentials, free energy, and equilibrium. So think about voltage, Ecell, free energy, Gibbs free energy, and equilibrium constant, K. And actually, it's not until the next video, the next lesson, but the Nernst equation to determine for non-standard state conditions. So when I say Ecell is equal to cathode minus anode, and you see these supernauts, those represent standard states. What if we're not at standard states? I need to show you an equation to calculate for non-standard conditions. But let's focus first on free energy, voltage of Ecells, and the equilibrium constant. We know that standard free energy, called Gibbs free energy, was defined as the maximum work that could be performed by a system. And I know that work for redox reactions is associated with the transfer of electrons from reactant, from what's being reduced to what's being oxidized, a transfer of electrons. And all I really need us to walk away from here, redox reactions are defined as the transfer of electrons. That's work being done through an electrical circuit. The work associated with transferring electrons is determined by the total amount of charge, which are coulombs, transferred, and the cell potential. Important equation. Gibbs free energy can be found by setting equal negative N F Ecell. What's N? N stands for the number of moles of electrons being transferred in your redox reaction. If I see an iron +2 plus a copper going to a copper +2 forming an iron, what's N? How many moles of electrons are being transferred? Well, the net charge over here is +2. The net charge over here is +2. We've had 2 moles of electrons being transferred. If I see 3 magnesiums plus aluminums going on to make 3 magnesium ions and 2 aluminum atoms. What's the net charge? 2 units of a +3 is +6. 3 units of a +2 is a +6. How many moles of electrons were transferred in that redox reaction? 6. It's the net charge from the balanced equation that allows me to find the N, number of moles of electrons being calculated. F in our equation stands for Faraday's constant. Faraday's constant is given to you. You don't have to memorize it. I have it on your equation page. 96,485 coulombs per mole. And of course, Ecell is the standard cell potential, cathode minus anode. You may find these equations on this slide enormously helpful to write down, especially this pyramid that allows me to exchange very quickly between equilibrium constants, Gibbs free energy, and the standard table of reduction for Ecell, the voltage of a battery. Delta G can be found by knowing negative RT ln K. R is the ideal gas constant. R is 8.31 joule per mole Kelvin. Oftentimes, delta G is given to you in kilojoules. So if you're using kilojoules, make sure you use 0.00831 kJs per mole Kelvin for your R. You want to make sure that you have like units. And of course, T, you know, has to be in the Kelvin scale. K is your equilibrium constant. Ln, of course, natural log. Ecell can be found in turning into equilibrium constant with the following equation. RT and F. What are those standing for? R is the gas constant. So again, you need to use 8.31 joules per mole Kelvin. Do you remember the definition of a volt right here? Because that's what Ecell comes to you in, doesn't it? What's your definition of volt you wrote down a little minute ago? A volt is a joule per coulomb. So if you put a joule per coulomb in for Ecell, you have to use 8.31 joule per mole Kelvin. N is the number of moles. F, of course, is the Faraday's constant. Delta G is equal to negative NF Ecell. N, the number of moles of electrons transferred. F is Faraday's constant. And again, as you digest these, it just takes practice. I've given to you this equation page, but I'm just saying the more you look at it, know where to find the formulas. I don't ask that you memorize the formulas, but know where to find them, the better off you'll be. I'd like to just practice. You can pause if you need more time to write these in your notes, but I'm going to move on to a practice and kind of put these thoughts together. K is the equilibrium constant. If it's greater than 1, we know it favors products. If it's less than 1, we know that it favors reactants. And if it's exactly equal to 1, you're at equilibrium. What about delta G? If delta G is negative, we know that the reaction is spontaneous in the forward direction. If we know that the standard cell potential is positive, we know that it's spontaneous in the forward direction, that you're favoring the products. If we're favoring reactants, we know it's a non-spontaneous reaction. If we have a positive delta G, it's non-spontaneous, and therefore you would have a negative voltage. If the Ecell is 0, delta G is 0, the equilibrium constant is 1, you are exactly at equilibrium, where the concentrations of product over reactants are the same, giving me a ratio of 1. Let's try a couple together and we'll wrap up our lesson. It says, using data from Appendix L. I want you to realize that that just means your standard table of reductions I've provided for you. The standard table of reductions. And these are not part of the test problem. You have to go in and find those from your standard table. So it might be helpful to just have that table printed and leave it on your desk. We're going to calculate the standard cell potential, standard free energy change, the equilibrium constant, all at the following conditions. Alrighty, let's take a look at what we have. Silver plus 1 is going to silver element. A plus 1 going to a 0 is more negative. This means that that is the reduction half reaction. Reduction occurs at the cathode. I've clipped this out and just pasted it here to save us time from going into the chart. You will need to go into the chart and find the values to do your homework. Or in Alex, you'll just click the table and look them up. Iron is going from a 0 to a plus 2. That is the oxidation half reaction, which occurs at the anode. We can calculate Ecell by taking the value of the cathode potential minus the anode potential. So Ecell 0.7996 minus negative 0.447. These are volts. Ecell comes out to be, excuse me, do you have positive 1.2466 volts? And as soon as I wrote down that it was a positive number, you know that it will be spontaneous in the forward direction. And what else do we know? Because it's spontaneous, I know delta G better come out negative, and I know that the equilibrium constant better be greater than 1, because those all mean the same thing. We're favoring the forward direction. Let's calculate delta G next. Go to your equation page and decide what equation would be most helpful. We have Ecell and are being asked to calculate Gibbs free energy. Negative NF Ecell. That's going to allow me to convert the standard reduction value that we just solved for to Gibbs free energy. What is N in our equation? Well, what's the charge on both sides? On the left side, we have 2 units of a plus 1, and on the right side, we have 1 unit of a plus 2. there were 2 moles of electrons being transferred in that reaction. So delta G will be equal to negative 2 moles of electrons times, do you remember Faraday's constant? Faraday's constant was 96,485 coulombs per mole. And the Ecell we just calculated, positive 1.2466 volts. But I want us to see this. A volt we defined earlier. Remember? A volt is defined as a joule per coulomb. And I'm writing that instead of the term volt, just to kind of emphasize unit conversion. Do you see in step 1, the moles canceled? In step 2, coulombs canceled, and now we're left with joules of energy. So I expect this to come out rather large. Sorry, I hit that instead of extend page. My bad. I'm going to hit 2 times Faraday's constant times the voltage. And remember that it's negative. So it's minus 2 times so it comes out to be negative 240,556.4. And that's large, like I predicted, because I'm still in joules. So just divide by 1,000 and you're more likely to see a kJ. How about if we do 240.6 kJs per mole? The mole canceled out, but this is typically what you'll have is just a kJ or a kJ per mole. Either would be acceptable. It's per mole of the reactant we're studying. All right, not bad, not bad. We got it. Last one we asked for was equilibrium constant, K. So with your set of equations, now that we know delta G, we know that delta G is equal to minus RT ln K. That's what we want to know, is the equilibrium constant next. Let me extend the page. Now here's my note from before. R can either be 8.31 joules per Kelvin mole or 0.00831 kilojoules per Kelvin mole. Alrighty. We can use the kJs, we just have to make sure that the R is going to match it. And I like to do it that way better so my numbers aren't so darn large when I plug them into the calculator. How about the temperature? You know, it never specifically said, but it kind of really did, because we're at standard states. And standard states say 298 or 25 Celsius, but we need it to be Kelvin. 298 Kelvin will always be used for the temperature in this equation. ln K. So I'm going to simplify, see if we can simplify this out. We have negative 2, I'm hitting this on my calculator, negative 240.6 divide by the product of R and T. When I hit that, I got 97.16 is equal to ln K. Let me just clarify, I did negative 240.6 over the product of 00831 times 298. I'll hit it again to be sure. Negative 240.6 divided by parentheses. Oops. And then I have 0.00831, 298. Yep, I got it twice, 97.16. So that E raised to the 97.16 gives me K. K better come out large because I know it's going to be a spontaneous reaction in the forward direction. So second function natural log of that answer, oh yeah, that's a big number. 1.57 times 10 to the 42nd power is your equilibrium constant. We have found K, the equilibrium constant. We found delta G, Gibbs free energy, all from knowing the standard voltage of your battery, Ecell. Once we know the standard voltage of a battery, we can find our formulas to find out Gibbs free energy, and we can find equilibrium constant from those relationships. And that's really the big practice, trying to go from one unit to the other with your equations. I'll end with this example, but I would encourage you to pause. Boy, this has been a long lesson, I know. Pause for a moment, give yourself think time, and then come back to the video when you're ready to check. Give me all three. I need Ecell, I need equilibrium constant, and I need delta G. I did the hard work for you, looking up the voltage from the standard reduction table. Okay, welcome back. I see that tin was oxidized, that 0 to a +2 was oxidation, so therefore I know oxidation occurs at the anode. I can see copper went from a +2 to a +1. That's your GR half reaction. Did you manage to grab the correct voltage? Because this was a little different, wasn't it? We went from a +2 to a +1. That voltage is 0.153, and that occurred at the cathode. So Ecell will be found by taking cathode minus the anode. 0.153 minus a negative 0.1375, 0.2905, and that's your voltage. I now know that this is spontaneous in the forward direction because I have a positive voltage, and therefore I know that delta G will come out negative, and I know that the equilibrium constant will be a large number, all saying the same thing. We're favoring the product side. I can find delta G next by taking. So let's test that N value. Sn is going to Sn plus 2. To balance that equation to the more positive side, I add 2 electrons to balance. Here we have Cu 2 plus pointing at Cu plus 1. To the more positive side, which is the left side, I would add 1 electron to balance charge. Now they're both plus 1s. Leo has to equal GR, so I know that I will distribute a 2 through that second half reaction. So how many electrons were being transferred is 2. There are 2 electrons being lost and gained in this redox transfer. So again, when I look at the overall charge, that's not always a guarantee. Make sure that you go through and look at the 2 half reactions to balance by charge using electrons to find N. The number of moles being transferred to, how about Faraday's constant? This is 2 moles, just to clarify, which was 96,485 coulombs per mole times the voltage we found was 0.2905 volts. A volt is defined as a joule per coulomb, and therefore I can see moles cancel, coulombs cancel, and you're left with joules of energy. That will be a large number simply because we're left in joules. You hit that with me and my screen said 56,057.785. So divide by 1,000, you get 56.1, we'll say, kilojoules for Gibbs free energy. And it's negative, I forgot to write that, negative sign because it is a spontaneous reaction. And the last one was the equilibrium constant. I would recommend using the equation that's easiest. Delta G is equal to negative RT ln K. Delta G, we just found that, didn't we? Negative 56.1 kilojoules times negative, remember to make your units agree here, 0.00831 kJs per mole Kelvin times temperature times the natural log of K. So take your kilojoules, divide out by the product of RT, take the inverse of your natural log to remove ln, and you will find that K comes out to be a value. My screen gives me a very large number. Let me see if I can write that neatly. 6,894,813,683. Holy mackerel, that's a large number. So I'm going to report that out using scientific notation. I'm going to round to just 2 sig figs. 6.9 times 10 to the 9th power, which is a very large K constant, and therefore favoring the product side enormously. We found the equilibrium constant, very large number, favors the product. We found delta G, a negative number, favoring product. And we found the standard cell potential, and when we found that, we knew it was spontaneous because of its positive value. Oh my gosh, a ton of good work. I celebrate you. Take a break. You have the last lesson when we talk about the Nernst equation and then electrolytic cells where we flip the reverse direction. So we've got one more video lesson after this one. Good work, gang. This was a long lesson. I applaud your efforts.